Now let us see what is the advantages and disadvantages of DC and AC drive systems. In the past, induction and synchronous motor drives were mostly used in fixed speed applications. Variable speed applications were dominated by the DC motors. But after the emergence of thyristors in 1957 led to the development of variable speed induction motor drives in late 60s, which were efficient and could match the performance of DC drives. Consequently, because of these advantages, squirrel cage induction motors were spreaded over the DC motors, and it was predicted that induction motor will replace DC drives in a variable speed applications. So, as of motor is concerned, DC motor require very frequent maintenance. DC motors require very frequent maintenance, whereas AC motors they require only less maintenance. They are very heavy and very expensive, and these motors, AC motors, are light and very cheap, and it can be operated only at a limited speed due to mechanical construction. They can operate in a very high speeds achievable, especially squirrel cage induction motor, and they are more robust when compared with the DC motors. And when I have a control unit comparison between DC drives and AC drives, they are simple and cheap control. DC motors are very simple and cheap to control, and even for high performance drives they are very cheaper. And decoupled torque and flux control. The DC motors are decoupled, have a decoupled torque and flux control. Say for example, if I increase the load on a DC machine, only armature current reflects. There will not be any change in the field current. When I want to have a flux weakening operation, only field current increases or decreases, whereas there will not be any change in the armature control. So there is a complete decoupled control of torque and flux in the case of a DC drives, whereas in the case of a AC drives it is a coupled control. But nowadays the vector control technique has come, which makes the AC motor also as closely as to operate as like a DC motor, and it is possible that you have a possibility to implement it by using a simple analog circuit, whereas to implement the vector control techniques, which is very similar to that of a DC drive, for an AC motor we require a fast DSPs, and the complexity of the system and the cost increases with the performance. And performance wise, they have fast torque and flux control, and here I have a scalar control satisfactory in some applications, and vector control which is very similar to that of a DC motor drives. So nowadays AC motors are preferred over the DC motors because of the main reason that it is heavy and expensive. Now let us see the torque equation of a rotating machines. Fundamental torque equations of a rotating machines. The motor generally drives a load through some transmission system. For example, the motor may drive a load through gears, step up gears or step down gears, V-belts, crankshaft, and sometimes through pulleys also. While motor always rotate, the load may rotate or may undergo a translation motion. Load speed may be different from that of the motor speed. Not necessary that the motor and load has to be rotated at the same speed. Sometimes the load may rotate at a speed higher than the motor speed by using step up gears, or sometimes the load may rotate at a speed lower than the motor speed by using step down gears. And if the load has many parts, then the speed may be different at different parts, while some may rotate while other may undergo a translation motion. It's however convenient to represent the motor load system by an equivalent rotational system as shown here. I have a motor coupled to a load, and TE is the torque generated or developed torque from the motor in Newton meters, and TL is the instantaneous value of load torque, which is generally called as a resisting torque referred to the motor shaft in Newton meters, and omega m is the instantaneous angular velocity of the motor shaft in radians per second. Since TL is called as a resisting torque, always the direction of TE and TL will be opposite. Load torque includes friction and vintage torque of a motor. Motor load system is shown in the figure. Here TE is the motor torque in Newton meter, omega m is the angular velocity to the motor shaft in radians per second, and TL is the load torque referred to the motor shaft, which is also called as resisting torque. and J is the moment of inertia of the motor load system in kilogram meter square. So as per Newton's second law, we know that force is equals to mass into acceleration, that is F is equals to m into A, which is for linear translation system. But for a rotating system, force is nothing but the torque and mass is nothing but the moment of inertia and acceleration is d omega by dt. So by applying the Newton's second law to the motor shaft, we can write Te minus TL is equals to d into j omega by dt. With constant inertia, that is considering j as constant, we can write the expression 1 as Te minus TL is equals to j into d omega by dt, considering j as a constant, which is also equal to j into d square theta by dt square. That is, first order differential equation is for angular frequency, which is called as a velocity. The second order differential equation is for angle, which is called as a position. In the second equation, j into d omega by dt is called as torque component, which is also called as a dynamic torque because it is present only during the transient operation. Drive accelerates or decelerates depending on the whether T is greater than or less than TL, that is whether TE is greater than or less than TL. During acceleration, motor should supply not only the load torque but an additional torque component J into d omega by dt in order to overcome the drive inertia. In drives with large inertia such as electric trains, motor torque must exceed the load torque by a large amount in order to get adequate acceleration. In drives requiring fast transient response, motor torque should be maintained at the highest value and motor load system should be designed with the lowest possible inertia. Energy associated with the dynamic torque J into d omega by dt is stored in the form of a kinetic energy given by j omega m square by 2. During deceleration, dynamic torque J into d omega by dt is as a negative sign. Therefore, it assists the motor developed torque T and maintains torque motion by extracting energy from the stored kinetic energy. Now let us see the torque equation for rotating systems with gears. Different parts of a load may be coupled through different mechanisms. As I told earlier, it may be through gears, wheels, crankshaft, or even sometimes through pulleys. These parts may have different speeds and different types of motions such as rotational and translational. I am going to present here the torque equation for rotating systems with gears. It is especially used in low speed applications which uses gears to utilize high speed motors. Here we have two loads, load 1 and load 2. Load 1 is coupled directly to the motor shaft and load 2 is coupled through a gear with N and N1 as teeths. The equivalent moment of inertia between motor and the load 1 is J0 and speed as omega m and torque as TL0. The moment of inertia of load 2 coupled with the gear is J1 and omega m1 is the speed of the load 2 and TL1 is the torque required by the load 2. Now we have to couple this, we have to make an equivalent motor load system for the system which is having two loads, one connected with the gear and one directly through the motor shaft, which will be something like this, which will have a motor with torque Te, omega m as speed and TL as load torque, equivalent load torque, and J be the moment of inertia of the equivalent system. Gear ratio A1 is given by omega m1 by omega m, which is equal to N by N1, where omega m1 is the speed of the load which is coupled through a gear and omega m is the speed of the load which is coupled directly to the motor shaft, and N is the number of teeth on the gear which is connected directly to the motor shaft, and N1 is the number of teeth of the gear which is connected directly to the load 2. So neglecting the losses in the transmission, we know that kinetic energy due to equivalent inertia will be equal to the summation of kinetic energy of moving parts, that is half j omega m square, that is kinetic energy due to equivalent inertia, will be equal to half j naught omega m square, where j naught is the equivalent inertia of motor and load which are directly coupled plus half J1 into omega m1 square, where J1 is the moment of inertia of load 2 which is coupled through a gear, and omega m1 is the speed of the load 2 which is coupled through gear. So if I divide that entire equation by half J omega m square, then we will get the equivalent motor load inertia J, which is given by J equal to J naught plus J1 into omega m1 by omega m whole square, which is nothing but A1 square, where A1 is the gear ratio. Let eta 1 be the transmission efficiency of the gears. Now the power of the equivalent motor load system will be equal to the summation of powers at the loads, that is power at load 1 plus power at load 2. So T1 into omega 1 m, which is the power of the equivalent motor load system, will be equal to TL0 into omega m plus TL1 into omega m1 by eta 1, where T1 is the torque of the total motor load system, omega m is the speed of the motor coupled directly with the load, and which is equal to TL0. TL0 is the load torque of load 1 and TL1 is the load torque of load 2, and omega m1 is the speed of the load 2, and efficiency eta 1 is the transmission efficiency of the gears. Dividing this entire equation by omega m, will get the equivalent load torque TL as TL0 plus TL1 by eta 1 into omega m1 by omega m. We know that omega m1 by omega m is nothing but the gear ratio A1. Therefore, TL is equals to TL0 plus A1 into TL1 by eta.